Hi, I'm going to talk about my work on cardinality estimation today. So overall, what we try to evaluate is how to improve cardinality estimators for the particular purpose of core downstream query optimization task. So you would have a query like this with three tables, and one way to execute this plan would be join A and B first, then join C, and it has a particular cost. There's another plan like this. The decision made by the optimizer would really be comparing the cost of the intermediate results that are different, and those are often proportional to the cardinalities. And so, for example, the true cardinalities of these might be like this, and then plan one would be chosen by the optimizer. And instead of true cardinalities, of course, we would have some estimator provide these cardinalities, and Postgres could be one of the estimators. And then we'll get a plan that is chosen based on those estimations, and we'll execute the plan and evaluate the various models on the final runtime we get based on the plans that we get from estimators. So there's been a lot of recent work using ML models for the sort of cardinality estimation problem. And one big area has been data-driven, and another has been query-driven. Data-driven would sort of model the whole join distribution in the database, various tables, joins, and then so on. And query-driven would just look at a history of queries and kind of learn some regression functions of that. Here, based on one of these benchmarking papers, we compare various models and our model as well on a particular database. To the performance, this is the end-to-end query latency performance. Looks like this. So the data-driven models do quite well. They're actually really close to optimal performance. Our model sort of improves on MSCN, but the key differentiating factor between query-driven models like MSCN and data-driven models like graphical models used in FLAT and DB is that when you're modeling the data distribution, you need to model the whole database, which makes them robust, but the model sizes are huge, training times are longer, inference times are longer as well. So the query-driven models can be very lightweight, don't need to consider like basically the growing size of the database. It depends more on the history. And it's pretty good if queries don't vary too far from the history and can support sort of undefined operators, privacy preserving, and so on. But the big problem is that if queries are similar, it's good. But if queries are not similar, it can sort of fail in very surprising ways. And it's sort of hard to even define what are similar queries. Like, is a new column okay? How many new columns? What happens when there's new data? And so on. So we make an attempt to study these particular common changes in database workloads and focus on improving performance based on like sort of simple methods that can be easily applied specific to these kind of changes. To sort of construct our evaluation test bed and sort of to guide the techniques we develop, we consider three public IMDb workloads. And essentially, these are very different workloads, very different properties and sizes, synthetic versus automatically generated. And we sort of train on one of these workloads and test on other workloads. And we kind of can also take different versions of the IMDb database based on time. And by making these changes, we give us some sort of really challenging real-world examples where there is a clear drift. There are different filters, different columns being used, different join patterns, and we see where the models fail and how we can fix those. One surprising result is that even when training on Joblight, we are able to achieve pretty good performance on JOB, which is a much more complex workload, pretty close to true when the data is new as well, and when the data is stale, kind of it's still better than like without our techniques, but our performance sort of doesn't really improve on Postgres, and that's the area I think that's very interesting to explore still. So now I'm going to show some contrived but very specifically chosen examples to give you an intuition behind the ideas that we develop. Again, this is not very realistic, but hopefully the intuition kind of is easier to understand with these examples. at a very high level, all our sort of techniques are somewhat distinct but connected by a common pattern in which we consider what happens when a particular shift happens. So we consider what happens when you train on JobLite and test on JOB, and like what kind of changes are there in query patterns and in ground truth data and so on. And we try to be robust to these sort of changes by either changing the kind of features you use for the model at both training and inference, or on particular kind of training techniques that mimic the kind of inference situations we'll get. So as one example, we consider a table with two columns, A and B, which are highly correlated, and sort of consider queries trained on like 1,000 points as seen here, and just like range filters on both A and B. And the Messian model does reasonably well, improves on Postgres a bit. But as we improve and increase N, the Messian model kind of keeps getting better, has very large variance, and the Postgres model also gets worse because statistics get worse, but the Messian model is not able to keep up. Note that this is when it's trained on 1K points. So it maybe is overfitting to particular details that you see only when in 1K points, and not this general pattern that the distribution kind of is the same. And I think the most critical thing is Postgres estimates are provided as features to the neural net model. And the sort of consistent distribution is that Postgres estimates typically would consider these columns independent, and it would sort of underestimate these estimates by far. And so it would consistently be underestimating it. So one pattern that could be learned is just correct those estimates to be to be a bit of overestimates. And this sort of is one of the key things that we hope to achieve with this technique. So the featureization would be something like this. There's the database estimate, then there which column is there, which attributes are there, and some constants. What we do is we mask some of the features randomly, except the database estimate in each iteration, and we kind of just train the model as usual using backprop. And basically this will improve the importance of the final feature, the database estimate, and those weights would be stronger. The model would be more dependent on that. And as the data set size is increasing, those estimates are also being adjusted based on the latest version of the database statistics. And so it is possible for the model to learn this sort of pattern that the database is always underestimating, and that's the relationship in this particular workload. But there are also other benefits for it. One key benefit that we see more about in the more complex workloads is that they're missing features that inference, so like some new table join and so on. And this masking technique kind of simulates by hiding some of these query features during training. But we always have up-to-date database statistics. So even when there's some features are missing, the database statistics, they still tell us important information, and we keep them. And so we sort of rely more on those as well. And this kind of is helpful to both data update scenarios and sort of just changing query templates. Finally, there are some regularization benefits always associated with dropout, but only doing dropout is sort of not enough, as we would show in ablation studies. And so, for example, in the same model now, the robust Messian model does a lot better and consistently improves over Postgres. So that was one contribution. And the second sort of key idea was handling joins when we are changing these workloads. One thing that happens a lot as you go, for example, from JobLite to JOB is that the filters are on completely different columns, even on different tables. And so it's very hard to really generalize. And this sort of two-table join would kind of illustrate that. So this sort of selects some TV show and the cast members from that TV show. And so, the sample bitmap approach, which is one of the sampling featureization approaches, would keep sort of two independent samples. We'll convert them into bitmaps. Here, the cast info table has all ones because there was no filter on that, and title had a filter. So it's a mix of zeros and ones, and goes into the model, and the model learns based on sort of this kind of distribution of inputs that it sees. Let's say the filter in a test query is on the other table in the same join pattern. we could do this, apply the same thing, but now the bitmap cast info would have like some zeros and ones, and title would have ones. And this is sort of essentially completely different representation compared to training queries. This is out of distribution. We would not have any sort of expectations for the model to do well, or even basically be random and surprising performance for such a model. So what we do is that semantically, these are very similar queries because they're sort of filtering for similar things. It's just on different tables. And this is kind of conceptually equivalent to how a lot of databases implement sideways message passing to estimate cardinalities. But we just do it at the level of featureization. So for the model, and the view of the model for these queries would look similar. So what we do is that we keep samples on the join keys. These can't be independent, and that has some drawbacks, which we discuss in the paper. Then we select one sample out of this, which is unified by taking an intersection of these. And, that goes into the model. And sort of this representation, when we sort of shift filter to the other side, is kind of still consistent. And this is no longer out of distribution. And we can hope for the model to do reasonably fine in such kind of cases. And this is sort of critical to get performance that, to train on some very simple workload like JobLite, and for it to work on more complex workloads. Now we'll explore some of our main results. And so a sort of very summary figure is that like when we train on the same workloads, both the models essentially do well. There's no data drift, there's no query drift, and they both do, much better than Postgres too, which is critical. But as we change just the workload, for example, the MSCN model is less robust. There are various versions of this that we analyze in the paper is one example. And just changing the data has a similar effect too, while our models sort of consistently good across those cases. And then we analyze cases where we change both. And here in some cases, our model's performance degrades too, but it's never far from Postgres. It's sometimes better, sometimes a little worse. Then another key experiment we do is this careful ablation study with various techniques and featureization approaches that we had, and basically trained on JobLite and evaluated on CEV or JOB. One sort of key thing is about this join bitmap approach. So mentioned on JobLite, it's particularly important to have this sort of consistent features, because JobLite has random filters on columns that are not really used in CEV and JOB, and sometimes different tables too. And so removing join bitmap and putting in sample bitmap is disastrous. And there are sort of similar benefits in query for these query masking techniques too. Less on CEV, more benefits on CEV, where it's more complex kind of filters. Now, this was all showing final runtime results. Of course, we kind of really need to take a deeper dive into how things look for per query. So we have this sort of visualization where you can choose a test workload, one of the training workloads, and one of the models, and compared to the baseline. For example, let's compare it to Postgres to robust MSCN. Everything below 0 here is where our model is better. This is where our model is worse. And then there's a bunch where queries where the models are similar. You can click on one of these particular queries and see the performance and the query plans down here. And so you can see, for example, Postgres does really badly, spends 100 seconds on this plan. And this is where it's sort of estimating it to be 1,000 rows, but it's actually 100,000, and kind of leads to several bad decisions through this plan that leads to this join. While here, everything kind of runs fast, where it's choosing the correct join order. And yeah, you can explore the rest of the results here. And that's it. Thank you. Here are a few links.